Okay. So, this is one of my many favorite topics, enzymes. So, you cover enzymes supposedly in food chemistry quite a bit. Now here we're going to talk about the application of these enzymes and how they're used in food analysis. Okay, so from what you see here, what do you know which enzyme, guys, which enzyme we need to inactivate so that you keep the cloudiness of your juice? I would guess pectinase. Which pectinase? There are two types. There's pectinase that is actually a hydrolase that will hydrolyze the pectin. That's not the one. That's for clarification of apple juice, for example. Use pectin. Oh, Cindy knows the acid. Huh?
Yeah, what? It's not movable. Or movable.
Application of enzyme to this analysis.
It's not in. Not that anyone's been able to change.
That's not document analysis.
Because I have 2018.
Before fact characterization. Before. What is it? Cindy, you printed that. Where is it? You don't find it?
Yes. Sorry, that's a lot of them. I have 2018.
Yeah.
I have an old one.
You're all
Well, sorry. You're good.
I need to get post-it notes and put them here.
Yeah, I've explained it, but I feel like it's too late now.
It should be after carbohydrate, but you don't have it here.
No, it's not after carbohydrate in mine.
No. It should be, but it's not there. Nobody has it. So,
Do you want to just take notes for all of us and send it out? Send those screenshots? No.
so if I
Is this like the quiz Monday?
it's online. It's on Canvas.
Oh, yeah, he's driving 4 hours.
Okay.
I should have looked up part of it. Yes.
So it comes after carbohydrate in the PDF folder that I gave you, but you must have just forgotten to print it. Yeah. So it comes carbohydrate analysis, then application of enzymes. That's the order. Huh? Okay. Well, it's on Canvas. I don't know. It's not in here. I don't know what happened to it. But it is on Canvas. I post everything on Canvas. What is this?
You weren't lecturing. Yeah. I was like, yeah, geez, it's important.
Okay, going back. So if you have your laptop and you want to follow, it's on Canvas. Okay. All right. So I was asking you what enzyme you need to inactivate to maintain the cloudiness of your orange juice. It's not pectinases. Pectinases are hydrolases that will break down the pectin, and it's used to clarify apple juice. Break down the pectin, apple juice, and then you get a clear juice. Here, it's pectin methyl esterases. So in this, you deesterified modify your pectin monomers, which are the lacturonic acid, sometimes have a methyl group. So when you break up the methyl group, the carboxyl acid will be ionized. And then if you have calcium added to your orange juice, it will form polymers through calcium bridges, and it will fall out. And then you lose the cloudiness in your juice. So you want to inactivate that enzyme and then measure the activity of the enzyme to make sure that it was inactivated. Okay, so what makes this syrupy in the chocolate-covered Cheerios rather than crystalline? What kind of sugars do we use here? So, sucrose, does it crystallize over time? Yes. Okay, so it crystallizes. However, if we use fructose and glucose, if we take that sucrose and we use invertase, I'm going to get glucose and fructose. Glucose and fructose will have like the syrupy texture, and they will not crystallize over time. Okay, so that is a use of another enzyme. Why do I have this corn here? High fructose corn syrup. Okay, so I take cornstarch, I break it down all the way to glucose, and then I use isomerase that will convert glucose to fructose and give me the high fructose corn syrup that is used as a sugar added ingredient for sugar addition. Okay, another important enzyme in flour is alpha amylase. So if I have high activity of alpha amylase endogenous, what's going to happen is going to chew up my starch. And then when I use the flour to build viscosity, the viscosity will not be built as much because of my starch being hydrolyzed a lot by the alpha amylase. So alpha amylase activity in flour is an indication of starch functionality, is an indirect indication of starch functionality. These are just examples here. Let's talk more about other examples where enzymes are important in food analysis or food systems. In food systems and analysis. Can you think of other examples where enzymes are very important to us? Okay.
Shelf life.
Shelf life. What types of enzymes? Oxidative enzymes, like lipoxygenase, is very important. It might cause oxidation of lipids. Very good. So quality. What other examples can we have?
Starch analysis.
Starch analysis, exactly. So it's used for quantification of constituents. Very good. Cici, you were looking at me. Do you have an answer? No? You were just looking at me. Okay. All right. What else? There's a lot of different examples. Yes? Huh? Lipid hydrolysis, yes. So hydrolytic acidity, of course. Food quality, again, quality. What else? There's a lot more. I'm going to pull them one by one from you. That?
Oh, to make cheese.
Make cheese, processing tool, rennet, very good. You have your hand up. Yes. Huh? Color? Color development, right? Yes. Okay, yeah. Like the, what is it called? Polyphenol oxidase. Can result in brown color. Again, quality. We said quality so far, processing tool, Jason. Huh?
Tenderization.
That means tenderization, processing tool. Another example of processing tool. You use papain and bromelain to tenderize meat. Okay, yes.
Like enzyme digestion.
Enzyme digestion for what purpose? Yeah, well, we have enzyme hydrolysis. You can produce protein ingredients like protein hydrolysase. You can also use enzymes as preparatory step. So when you want to determine total dietary fiber, we explained that last time, we used amylases, glucoamylases, and proteases to break down all the carbohydrate and proteins, and the remaining would be your fiber. Okay, there is a couple more, like when you blanch your vegetables or whatever. So what's the blanching for? During processing, of course, many of you have taken food processing already. Yeah?
Inactivate.
To inactivate enzymes. So when we blanch, we need to test if we got rid of our enzymes. So usually we either test lipoxygenase or peroxidase, because both enzymes are heat stable. So if we inactivated peroxidase or lipoxygenase, that means all of other enzymes have been inactivated. Okay. Do you remember the test to determine the efficiency of milk pasteurization? Have you heard of the enzyme that we test to determine pasteurization? Gosh, I'm blessing on it. What is it? Why am I blanking? Alkaline phosphatase. It came back. So alkaline phosphatase is the enzyme that you would measure in order to determine the efficiency of pasteurization. Why? Because if you pasteurize the milk and you want to determine if pathogens have been killed, instead of doing a microtest that can take 2 days to get results, you would determine the activity of alkaline phosphatase, which is more stable than any pathogen. So if the alkaline phosphatase has been inactivated, that means all of your pathogens have been inactivated. Okay. So many of what we talked about falls under food quality, processing tool, we said sample preparation, quantification of food constituents, measuring activity, we talked about lipoxygenase for blanching, alkaline phosphatase in milk, rennet activity to determine how much rennet I need to add to the milk to produce a certain amount of curd, to determine the activity of my rennet. And then waste management. So sometimes you have streams that have potentially some protein, lipids, and carbohydrates in them, the waste streams. So you don't want to clog your waste drainage, so you would use enzyme to hydrolyze everything to kind of not clog your system, your pipes. Okay. So because we use enzymes in so many different applications, whether to determine constituents or use them as a processing tool, so I need to measure the activity so that I know how to use them. So in order to determine the activity of the enzyme or the constituents that are measured due to enzyme activity, we really need to characterize them by understanding enzyme kinetics. Your favorite subject. Is it not? Have you done enzyme kinetics in food chemistry yet? Okay, so it's not a foreign topic. I will introduce it again, but for the purpose of using it in analysis. So I'm not going to go deep into it like you would in food chemistry. So, as a reminder, when you have an enzyme in your system and you have a substrate, they're going to bind to form a complex, enzyme substrate complex. So K1 represents the rate constant for this complex formation. But this can be reversible. ES can go back to E plus S. So this is the reverse, the rate constant for the reverse. But ES can go forward and produce a product and release the enzyme so that it can go back and interact with substrate. So going from ES to E plus P is the constant of the conversion to product. So by definition, enzymes are catalysts. They're biological catalysts. So that by being catalysts, they are reducing your activation energy to induce the reaction to go forward with less energy needed. Okay? So two events: stereochemical binding, very specific binding of a substrate and an enzyme, and then a chemical conversion occurs since you have reduced the activation energy. Is your next best figure here that you really need to understand. It's important to understand because this is a big part of analysis when we're dealing with enzymes. So when we have an enzymatic reaction, oftentimes you are monitoring the concentration of a product that is generated. And you can monitor that mostly by measuring absorption. So you're always monitoring most of the time your product. So P stands for product. Over time. So how much you're producing over time. The slope of that is your rate, reaction rate. Okay, but if we look here, there are three compartments. There's the pre-steady state, the steady state, which is linear, and then it curves. So pre-steady state, it's milliseconds when the enzyme is really binding to your substrate. And then here, the steady state is the rate of disappearance of ES. That means K minus 1 plus K2 equals the rate of appearance, which is going into ES. That's steady state. Appearance, disappearance equal. We have a steady state, and it's a linear relationship between the product and time. So the slope of that is your initial velocity. Okay, so slope is the V0 or initial velocity. What's happening here? Why does it curve? I'm sorry. He doesn't know. No, you don't know this. I'm not saying that. You just said, okay, you have your hand.
All the enzymes are saturated.
All the enzymes are saturated. Not quite. Okay. We ran out of substrate. So here, then we are no longer in steady state because we don't have as much substrate to be the rate of disappearance or rate of appearance. So now the rate of the production of P is reduced until it becomes 0, nothing. Okay. So that's the initial velocity. Like I said, it's the slope following the pre-steady state. In this case, where we have linear relationship between product and time. Okay, so what's maximum velocity? I'm just trying to remind you of the different terms because you would need to understand the different terms. So maximum velocity is when you saturate your enzyme with the substrate. That means when you have a lot of substrate, so your concentration is high here. So this, what is this graph? This is substrate concentration against your initial velocity. So how do you get this graph? How do you obtain it? You would run multiple enzymatic reactions at different substrate concentration. So you will start with substrate concentration x1, and you run it, and you monitor it over time, and then you start with substrate concentration 2, and you run it, and you get, at each time you get your initial velocity. You get the slope each time, and you plot that slope against the different concentrations that you use. And then when you plot it, you see at some point you won't see any more effect. You reach maximum velocity, and then it doesn't change anymore. That's because this enzyme is saturated by the substrate. It's no longer impacted by the substrate concentration. So really here, it's 0 order with respect to your substrate. Okay, so try to remember when your reaction is no longer impacted by the substrate concentration, it's zero order with respect to the substrate. Okay? So that's where you get to Vmax, velocity of the reaction at very large substrate concentration. Now, Km is another beautiful term that tells us a lot of information. So Km is Michaelis constant, but what is it really? Now, when I ask you in an exam, what is Km, you tell me Michaelis constant. Okay, what does that mean? It doesn't tell me anything. You just named the person that named it. But what is it? It is the substrate concentration, Km. It's on this axis, right? So it is the substrate concentration where I have my velocity is half Vmax. So half the maximum velocity. So it's the concentration of the substrate, I have half the maximum velocity. Okay, why is this important? Oh, it tells me a lot of different things. One important thing, it's going to tell me the affinity of the enzyme to the substrate. So how much the substrate is liked by the enzyme or reacts readily with the enzyme. So if I have, so I'm going to draw this again, V0, and then here's your substrate concentration. And then I have this, and then I have this. So this is Vmax. This is half Vmax. So two substrates, substrate 1, substrate 2. And one enzyme, enzyme X. Which of these substrates, which the enzyme has a more affinity to? S2 or S1? Think about it and tell me. The enzyme has more affinity towards S2 or S1? Sophie, you want to say something?
Sure. S1.
S1. Why? Can you explain?
Because even at a lower concentration, it's reactive.
Exactly. Because S1, we got to V, which is Vmax over 2 here. This is just the y-axis, it's V0. So here, at lower in substrate concentration, I got to half the Vmax. Here I needed more than double the concentration in this graph to get to Vmax over 2. So obviously the affinity for S1 is much more than the affinity for S2. Okay. So I might ask you in the test, what would be the factors that impact the affinity? What would be factors that impact the velocity, the maximum velocity? So there are so many factors related to the substrate and enzyme, and then factors related to the environment. The pH, is it optimum? The temperature, is it optimum? Are there any inhibitors in the system? And same here for Vmax. The only difference, instead of the enzyme nature, it's also enzyme concentration impact the Vmax. So the higher the concentration of the enzyme, the higher the velocity. If we have saturation with substrate, if we have enough substrate, the more concentration of the enzyme, the higher velocity we are going to reach. Okay. So again, I explained these terms to get you to the analysis piece of things. So if I want to measure substrate, so if I want to measure glucose, for instance, or ethanol, or whatever, sulfite, whatever I'm looking for to analyze using enzyme reaction, I want to measure the substrate. That means I want my reaction, or my rate of the reaction, to be affected by the enzyme concentration. That means to be first order with respect to the substrate. Okay? That means any change in the substrate will result in a change in the rate of the reaction so that I can measure that. Okay? So in this case, I want to prepare my assay where my substrate concentration is much less than the Km value. So this demonstrates that you really need to know the Km and Vmax of your enzyme towards that particular substrate. If you don't know these information, you cannot construct your enzyme assay. Okay? So it's very important that we know the Km of our system, substrate and enzyme. Okay? The same enzyme with different substrate will have different Km, so it's very important that I know that. So I want to have enough enzyme in the system so that my reaction is zero order with respect to enzyme. So my enzyme should not be the limiting factor, but my substrate should be the limiting factor. Okay? So first order with respect to substrate, zero order with respect to enzyme. I need to have enough enzyme to measure my substrate. Flip it. If I want to measure enzyme activity, now I don't want the substrate to be the limiting factor. I want the rate of my reaction to be impacted by the enzyme activity so that I can measure the enzyme activity. So in this case, I need abundance of substrate. I don't care about the substrate concentration. So I need to put a lot in there so that my enzyme is saturated and any change in the rate is impacted by the enzyme, not by the substrate. So when I'm measuring enzyme activity, I need to be here. When I'm measuring substrate, I need to be up there. Okay? So I want it to be here in this case, the zero order with respect to substrate, and first order with respect to enzyme. That means it's impacted by the enzyme activity or change in enzyme activity. Okay. So by telling you I need to know the Vmax, I need to know the Km at particular enzyme substrate combination. How do I do that? Michaelis-Menten equation. So what they did is they plotted the velocity against the substrate concentration and came up with the equation of this curve. But we don't like nonlinear curves. We prefer linear curves in our calculations. So what they did to convert that to a linear curve, they inversed it. And came up with the Lineweaver-Burke plot. Two other people inversed it. So another scientist, Lineweaver-Burke, they inverted that equation, the Michaelis-Menten equation, and they came up with a straight line. And this is your regular regression line, linear regression line, where your y, which is you would measure from your reaction, you would actually measure the concentration of the product over time, so you can get the velocity, initial velocity. So you have this value. And then you're searching for the Km and Vmax. But you have the concentration of the substrate. 1 over S is the concentration of the substrate. And then 1 over Vm is your intercept, right here. So this is your intercept. So from your equation of the line, you can get the intercept. Therefore, you can calculate Vm. And Km over Vm is your slope. So if you have the Vm, you can calculate the Vm. So there you go. So you design your equations or chemical reactions, enzymatic reactions, so that you can get the slope at different concentrations Vmax and plot that, and then you can calculate Km and Vmax. Easy. Any questions? Smiling. Okay. Recap questions for later. Okay. So now let's talk about factors impacting the rate. As I said, as you increase enzyme concentration, your rate, your velocity increases. That is an obvious impact of the concentration of the enzyme. However, we have to be careful with selecting the enzyme concentration because, and the time of the reaction, two things that we really need to be careful when we design enzymatic reactions. We need to select a time that is meaningful in a way that it's not too short and not too long. So you can't have an enzymatic reaction that's 15 seconds because then you won't have time to actually do the measurement. And you don't want a reaction that's 2 hours, that's too long. So you want to select a time that is reasonable, 20 minutes, 10 minutes, the reaction time. So that is important. Concentration of the substrate is important, and what enzyme concentration I use so that my prediction remains linear at that time point. So if I look at concentration of the enzyme 3, what happens here over time, I'm depleting the substrate really fast. So if I deplete the substrate really fast, the actual change is this. This is the predicted, but this is the actual because I'm running out of substrate at this concentration of enzyme very fast at this time point. So that is my prediction is not accurate. This is the linear prediction, this is the actual. However, at concentration 2, I still get a linear relationship, which is the predicted is the same as the measured. So this seems to be really good concentration. This is too slow, and then you won't get a detectable measure. With the first concentration, your product will be too low of a concentration at this time point. You won't probably get absorption that are very low. So it is better to go to something that is moderate, gives you enough detection in that time point, and remains within the prediction. Here we are going away from the prediction, and with much higher concentration of the enzyme, we are really going away from the prediction here. So if I want to stay in the linear, right there, the time might be like 10 seconds, which doesn't make sense for me when I'm running an analysis or an enzymatic reaction. 10 seconds is terrible. So you want to make sure you have enough time to do your measurement and the right concentration so that you remain within the prediction. All right. The other important factor that we want to control when we're designing our enzyme reaction is our temperature. So every enzyme has an optimum temperature. So this is the velocity and this is the temperature. So I don't have here really numbers because your temperature for an enzyme that is optimum can be 37, like the body temperature, or it can be 55 or 60 or even 70. Some enzymes, especially microbial enzymes, have higher temperature, optimum temperature. So as we increase the temperature, your activity, the kinetics, increase. So you have reached an optimum temperature where you have maximum velocity. However, well, theoretically, you would say as I increase the temperature, the reaction is going to go more and more and more. But it's not the reality because what happens to the enzyme when you increase the temperature to high temperatures? It's denatured, it's a protein. So at one point, your enzyme will be denatured. Again, each enzyme has different denaturation temperature. Like any protein have different denaturation temperature. Some enzymes denature at 70, other enzymes you need to boil for a long time until you can get it deactivated. Okay, so it's really the choice is dependent on the enzyme, or the behavior dependent on the enzyme. pH. pH is another important factor that when we design our enzymatic reaction, we have to look at what's the optimum pH for my system. Why is pH important? Because the pH dictates the ionization state of your protein, which is the enzyme in this case. So changing in pH will change the ionization of the different groups on the protein. And by doing so, it will impact how that enzyme is going to react with the substrate. Do we have the right ionization state for the binding to occur? So at optimum temperature pH, well, in this case pH 6, but it's not always optimum pH 6. Some enzymes have optimum pH that are acidic. Can you name one that has an acidic optimum pH of 1.6 to 2? We all have that enzyme. We walk around with that enzyme. Becomes very active when we eat. Yeah, what is it? Pepsin. Pepsin has a very low optimum pH. So each enzyme has different optimum pH due to the ionization state, and then it would bind to its substrate at that ionization state. As we go away from that pH, then the activity drops. There is a difference between inactivation of the enzyme and stability of the enzyme. So if we go down, for example, for trypsin, if we go down to pH 3, it's not very active, it's not active, but it is not denatured. So if we bring it back to pH 7 or 8, it's going to be active again. Other factors that impact our enzyme reaction, some enzymes need activators. Prosthetic groups, that are groups that bind strongly to the enzyme. It could be organic, like vitamins, sometimes can act as activators. Or it could be inorganic, like metallic ions. Sometimes you need iron. Sometimes you need chloride or sodium for the enzyme to work. Coenzymes, they dissociate and associate, so they don't bind that strongly. And sometimes, well, chloride is here actually, not up there. And NAD is an enzyme activator in some cases. Enzyme inhibitors, irreversible, and once they bind, they don't dissociate very easily. It's like alpha amylase inhibitor is an irreversible inhibitor. And then you have the 3 different forms of reversible inhibitors. Competitive, competing for the same binding site. Non-competitive, they bind at a different site, but they change the binding site. And uncompetitive, they bind to the ES complex. So once the ES complex is formed, they bind and then they prevent the change in the reaction to happen. Okay, so you should have learned more about these with examples in food chemistry. All right, with this introduction, now we'll go a little bit into the actual analysis. So when we analyze the enzymatic reaction, mostly it's absorption spectroscopy. So absorbance, sometimes it's fluorescence. So absorption, fluorescence, spectroscopy are the main ones, with absorption being the main. Other means for enzymatic assays, manometric for pressure, changes in pressure. Let's say uptake of oxygen, for example, by glucose oxidase. You can measure that by change in pressure. Titration, isotope measurement, changes in viscosity. But there are less common methods than measuring absorption. We talked about coupled reactions last time. So oftentimes in analysis, we have coupled reactions. The first reaction is our measuring reaction or auxiliary reaction, where you